what it feels like to be weightless, to float freely in space, unburdened by the invisible pull of gravity. Imagine being in a place where the forces that keep us grounded are non-existent. This is the realm of zero gravity, a concept that both baffles and intrigues us. However, there's a common misconception that space is completely devoid of gravity. This, my friends, is far from the truth. Well, according to Einstein's theory, you might be surprised. Albert Einstein, one of the greatest minds of the 20th century, had a lot to say about gravity in his general theory of relativity. Now, you might think of gravity as a force that pulls you down to the ground, right? Well, Einstein had a different take. He proposed that gravity isn't a force at all. Instead, it's more like a curve in the fabric of space and time, which he collectively called space-time. Think of space-time as a trampoline. If you place a heavy ball in the center, it will create a dip or a curve. Now, if you roll a smaller ball onto the trampoline, it will roll towards the heavier ball. Not because there's a mysterious force pulling it, but simply because the path it's following is curved towards the heavier ball. In the same way, the Earth is like the heavy ball creating a curve in space-time, and we are like the smaller balls rolling around on that curve. It's not that there's a force pulling us towards the Earth. We're just following the curve in space-time that the Earth creates. Now, where does energy fit in all this? Energy and mass are two sides of the same coin, according to Einstein's famous equation E=mc². This means that anything with energy also contributes to the curvature of space-time. So even light, which has energy but no mass, can be bent by gravity. And what about zero gravity? Well, that's a bit of a misnomer. Even in space, where it feels like there's zero gravity, there's still a curve in space-time. Astronauts in orbit are actually in free fall, constantly falling towards the Earth, but also moving fast enough sideways to miss it. That's what gives the feeling of weightlessness. So in a sense, when we talk about zero gravity, we're really talking about free falling. Now here's where things get a bit tricky. Let's dive into the paradox of weightlessness. It's an incredibly fascinating concept, and it's a bit like trying to catch your own shadow. Imagine this: you're an astronaut floating in the vast expanse of space. You're not standing on solid ground, and you're not sinking or rising. You're just there, suspended in the void. You'd feel weightless, right? But here's the catch. You're not actually weightless. You see, astronauts in space are constantly falling towards the Earth. Yes, you heard that right, falling. But why don't they crash? Well, it's because the Earth is also moving. Earth's curvature changes as the astronauts fall, so they keep missing it. It's a bit like trying to hit a moving target while you're also on the move. Now, you might be wondering, if they're constantly falling, why don't they feel it? That's where the real paradox of weightlessness comes into play. They don't feel the sensation of falling because everything around them is also falling at the same rate. Their spaceship, their tools, even the coffee in their space mugs, everything is in a state of free fall together. This creates an environment where there's no up or down, no heavy or light. There's just nothingness. But it's not the eerie, void-like nothingness you might be picturing. It's a state of continuous falling, where the normal rules of gravity seem to have taken a vacation. This experience, this sensation of falling without feeling like you're falling, is what we refer to as weightlessness. But it's not because there's no gravity. Oh no, gravity is very much at work here, pulling everything towards the Earth in a never-ending cosmic dance. So when astronauts float around their space shuttle, seemingly defying the laws of gravity, they're not really defying anything. They're just living in a world where everything is falling together, uniformly, creating the illusion of weightlessness. In other words, they're experiencing what Einstein would call zero gravity. So what does all this mean for us back here on Earth? Well, let's dive into the implications of zero gravity. First of all, the idea of zero gravity isn't just about floating around in space, sipping Tang or playing catch with globules of water. It's a lot more serious and fascinating than that. For starters, zero gravity has a profound effect on the human body. In the absence of gravity, our bodies undergo a series of physiological changes. Our muscles and bones, which are used to constantly working against Earth's gravity, begin to weaken and lose mass. This is why astronauts need to exercise rigorously during their stay in space to counteract these effects. Moreover, our cardiovascular system also gets a bit confused. On Earth, our hearts pump blood upwards against the pull of gravity. But in space, without gravity, the heart doesn't have to work as hard, which can lead to a decrease in heart muscle mass over time. Now, the effects of zero gravity on the human body are not just a concern for astronauts. They're a puzzle for scientists too. Understanding these effects can help us prepare better for long-duration space travel and perhaps future colonization of other planets. But that's not all. Zero gravity also has implications for scientific research. In a zero-gravity environment, we can conduct experiments that would be impossible or highly difficult on Earth. For instance, studying how fluids behave without gravity, or how fire burns in space can lead to breakthroughs in various fields, from medicine to material science. Furthermore, zero gravity allows us to observe the universe in ways that are not possible from Earth. By escaping the distortion caused by Earth's atmosphere, we can get clearer, more precise views of distant celestial bodies. So, as you can see, zero gravity isn't just about spacewalks and floating astronauts. It's about understanding our bodies, our world, and indeed our universe in entirely new ways. Indeed, the concept of zero gravity is much more than just a fun thought experiment. So next time you see an astronaut floating in space, remember, it's not because there's no gravity. Let's take a step back and revisit the concepts we've unpacked today. Einstein's theory of general relativity, a cornerstone of modern physics, redefined our understanding of gravity. Instead of viewing gravity as a force pulling objects towards each other, Einstein proposed a radically different perspective. He posited that massive objects cause a distortion in space-time, which we perceive as gravity. The Earth, for instance, creates a sort of dent in the space-time around it. Objects then move along the curves of this dent, and this movement is what we experience as gravitational pull. This brings us to the concept of weightlessness or zero gravity. The term can be misleading. It's not that gravity has magically disappeared in these circumstances. Rather, what we're witnessing is a state of continuous free fall. Picture an astronaut aboard the International Space Station. The station is constantly falling towards the Earth due to gravity, but it's also moving forward fast enough to keep missing it. So the astronaut and the station are falling at the same rate, creating the illusion of weightlessness. You may be wondering, why does this matter? Why do we need to understand these abstract concepts? Well, these theories have practical implications that extend beyond the realm of academic curiosity. They underpin the technology that enables GPS navigation, and they guide the calculations for space travel. Understanding these principles is crucial to advancing our exploration of the universe. So, in essence, Einstein's theory tells us that gravity is not an invisible force acting at a distance, as Newton proposed, but a result of the curvature of space-time caused by mass and energy.